Um, this video is about redoing the lecture on September 28 for electrochemistry course. I'm going to review a bit of the material explaining about the energy diagram of an interface between a metal and semiconductor. After that we'll focus on the interface of the electrolyte energy structure, including for a case with a metal electrode and an electrolyte, and a case with semiconducting electrode and electrolyte. So very quick update. A part of the discussion was on basic semiconducting devices and the energy diagram of them. So I'm going to use a little bit of the as a tool. I'm going to write something on the board behind me, and I get sure that the video will capture that. Also slides are available on the second screen, so I will switch the camera between the monitor and the whiteboard, so we can have everything on the video. Although this is supposed to be about 40-45 minutes of the lecture that I'm redoing, I'm going to break it to a few videos each for less than 10 minutes, so it would be easy to upload it on YouTube. In total it might be a little bit longer or even shorter than original lecture, but that's the focus will be on the content of the course, and I'm hoping that I will cover everything that's is missed on the online recording. So very quickly, we went for this part to trying to answer that there's a question about the semiconductor electrolyte interface. What we had was that we tried to add quite a few things over there, and we learned that maybe Schottky contact is the one that we have to look up. As a source for reading, this book is available on USF website, USF library website. You can search for that. Just to be clear about the part of the book that's related to the discussion on this course, you can read materials from chapter 2 section 1 and chapter 2 section 2, including the section 2.1 barrier height, and 2.2.2 majority carrier transfer processes. And also the second half of the lecture that's missing, the video is missing, and I'm recording that, is covered in chapter 6 section 2 6.2. The Grischer model explains a lot about the detail of the discussion of the semiconducting electrolyte interface. So on this we already mentioned about the energy structure of the metal, semiconductor, and insulators. There was a question about the application of Poisson's equation. In general, when we wanted to find out how electric field is distributed in space, and also how potential is changing in space, Poisson's equation can give us the full picture of the story. So in a Poisson's equation, in this case, as written on the board, it is electric field is described with E, and psi is the one that's the potential or electric potential with the unit of volt. So if we have some charge in a space, rho x, coulomb per centimeter cube, we can solve this Poisson's equation to get the answer. Well, the really short conclusion from this equation is that if we have some charge in space, so like a depletion region in a semiconductor, so the value of the rho x could be non-zero, and assuming it's a uniform charge distribution, so that would be constant, and that would result in getting electric field to be a linear function with x, and potential would be quadratic function of the x. That's a reason that when we look at the energy bending, we see that for the region that here I'm trying to catch that for the region that we have the depletion region, so we have charge in this part of the semiconductor because the electrons have left the semiconductor to get to the metal junction. So for this part, when we have some charge in space, the electric field is non-zero. It can be linearly proportional to x, but also the potential would be a quadratic function with x too. However, because potential and energy are kind of related, potential is expressed with a unit of volt, and energy is electron volt, so meaning that charge multiplied by potential gives us the energy. So we can see that the kind of the profile that the opposite way it is. So the profile that we see here, it's a quadratic function with x. So all the energies, the conduction band, valence band would be curved with the quadratic function of the x, and because we are drawing this diagram for the equilibrium condition, the Fermi level is straight across the junction. In the lecture I mentioned that this figure is presenting the surface state, and for that reason here is the vacuum, but you can cross this vacuum here, and if you have a metal, that's the Fermi level of the metal. The diagram is more or less similar to this. So there is a significant information that we can get from Poisson's equation, but since this course is not about semiconducting materials, and that needs a very detailed discussion, so this is just introduced. The Poisson's equation is just introduced to refresh our memory that the band bending happens in semiconductors when they make junction with the materials with different Fermi level. And if we wish to find the amount of the band bending and the depth of the depletion region, and also the capacitance that we get from the junction, all can be done by solving the Poisson's equation, and if we put the boundary condition on that, we'll find out that the barrier, the built-in potential across the junction would be simply the difference between the Fermi voltage, Fermi level in metal and Fermi level in the semiconductor. So subtracting those two Fermi levels would present the energy difference between those two, and if we divide them by the charge, the value would be equal to the voltage that we call it the built-in voltage. That built-in voltage can be used in equation like this, which again comes from after solving Poisson's equation. The voltage can be used in this equation to estimate the depth of the depletion region, or the width of the depletion region. So we want to know that when the charges is transferred from semiconductor to metal, or vice versa, to what extent this charge has been kind of penetrated through the material. So that would be the width of the depletion region, or a space charge region, and the equation describes the relationship between the parameter of the materials and the depletion width. Also, as you can see, there is a factor here saying that VBI minus V. So we can use the same equation to describe that how depletion width is changing if we apply some voltage to the junction. So if the junction voltage is kind of against the VBI, the barrier would be reduced, and therefore the depletion region would be reduced. whereas if the voltage is kind of enhancing the electric field in the depletion region or adding to the building voltage, so the depletion width would be increased. How we can really measure that, how this depletion region is a function of the material parameters described in the equation? The simplest way is to measure the capacitance of the junction, and from the capacitance of the junction, indirectly we can find the value of the W from the equation written at the bottom. So I'm gonna stop this video now and start another video for rest of the discussion.